Hello, 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 hello. Hi, 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 hi. Dun-dun-dun. Welcome, guys. It's 90 days, and today we are going to. What?
I've got this, which is obviously for a mouse, but I don't know which mouse it was for. I'm looking for one, but I can't find it for the mouse that I've got.
All right. Okay. So today is 90 days. 90 days. Ooh, very, very interesting times. Let's see what we have here. So we are going to study some trees. Learn about trees. Trees. I did some trees problem some time ago, but wasn't really enough. Right? I just solved I think a few tree problems. And the thing about trees is before this is one thing I just realized. Um Trees really have to have a lot to do with recursion. You need to be able to understand recursion before you can solve tree problems properly. So recursion is very important in this case. And I think it is crucial for us to understand recursion in order for us to start solving trees related problems. Let's see if I'll come here. Recursion. Recursion in Python. Need to understand this very well. Calling recursive functions. You know, so recursion is really important. I'll leave it as the. I like Geek for Greeks, but even W3 schools has very nice, you know, content on programming. Either of these resources are enough to learn about recursion, because recursion is actually important for us to solve trees related problem. So I'll put this in the description, um, and then we will so learn about recursion. I'll put recursion, learn learn recursion like this, and let's put this here. So I'll copy this link too, and I'll put this here as well, and I save. Hello, Rohit. Oh, it's been a long time. Yes. Wow. How are you doing? Thank you very much. Thank you very much. Yes, I think I it was about 2 weeks ago when I got 1,000 subscribers. Thank you very much. Nice to have you here again. All right. So, oh yeah. Okay, you were the one who sent the invitation on LinkedIn. That was like last month, I think. Let me check it again and see on LinkedIn. LinkedIn. I think I accepted your invitation. We even messaged each other. By the way, we have a new. I don't know if you are on Discord, but there's a Discord server you can join and meet other programmers as well. Let's see. Yeah. So our Discord server. Yeah, yeah, yeah. Where is the Discord link? I think I have it here. Yes, we talked. That was in May. That was in May. Yeah, I remember now. Nice to have you here again, right? All right, we shall continue our work. Um, Today we have a lot of things to do. Not a lot of things per se, but like we need to understand certain things. Recursion, trees, and what else? Solve some trees related questions. I think there are some. Um, okay, I just saw keyword arguments, and I don't remember the last time I used keyword arguments. Well, anyway, that's a topic for another day. We are not going to do that now. It's just something I just saw, right? Anyways, let's see. Let's do a quick recap on recursion and understand recursion a little bit, so that understanding the problems we're about to solve on trees will be easier, right? So let's say now we have recursion is a way to call a function repeatedly until you no longer you are no longer able to call it. So there is a base case for every recursive function, meaning once that base case hits, then the function stop calling itself. Otherwise, we'll end up calling the function over and over again, right? And we'll run into an infinite loop. So, which is something we don't want. Recursion is more like loops, let's say a while loop, but with a break in it, right? So the break is basically the base case for you to terminate the recursive call of the function. So here is what we have. We have recursion. Python also accepts function recursion, which means a defined function can call itself, right? Recursion is a common mathematical and programming concept. It means that a function can call itself. This has the benefit of meaning this has the benefit of meaning that you can loop through data to reach a result. Okay, that's let's see. The developer should be very careful with recursion, as it can be quite easy to slip into writing a function which never terminates, which is the infinite call of the function, or one that excess amount of memory or process power. However, when written correctly, recursion can be very efficient and mathematically elegant. And mathematically elegant approach to programming. So this is just a lot of talks. So let's see a an application of recursion. So you see this function here. It's a tree recursion, okay, or try recursion. If k is superior to 0, then result should be equal to k plus the function call again, k minus 1, right? Else result is equal to 0. Okay, so in this case, uh, let's just type this out and see. I'll open my code editor here, and let's use this playground, right? I'll erase everything we have here so that we have space to practice some recursive functions. So here's what we have. We can define a function. Let's call this I'll call this sum values, right? Sum underscore values. And this function takes an integer. I'll call value and set it to int, and we can just return a result int at the end of the day. So let's see. Now we want to recursively call this function, meaning we want to call this function by itself, right? And what we'll do is to return the sum of every value within this value we pass here, right? If you look at this here, you can see this is what they did. Result is equal to k plus the function call, right? And then we'll print results. So we can do this here. We'll say, okay, let's just say if our value is superior to 0, right, then we'll call the function, right? So say results. Okay, let's define results here. Results is equal to 0, and we'll say results. Hold on. Okay, we'll say result is equal to value, right, plus the result, sorry, the sum value. Let's call the function again. Sum values value minus 1. So value minus 1. So else, so I'll say else, let's just return 0. Okay, if the value is not equal to, just return 0, or just return the value, right? Let's just return the value. Otherwise, we can just when we are done calculating, right, we can return the results. Okay, so let's see, this is what happens. Now the good thing about this is, okay, you know what, let's set the result to be value and then return the result instead. So say results should be equal to the value and then return results. Okay, so I mean, we could just return value here, but I'm just trying to use this as an example. Now in the first call, when we call this function for the first time, so say some values, right, of 3. Let's print what this will give us. So print some values of 3. Now you can see we have 6. Okay, what I was actually expecting is to return, so we have value plus the sum value until the value is equal to 0, right? So if the value is equal to 0, okay, I'm trying to do this now. I say return results. Is print result here, right? So the recursive call is actually a bit tricky, but you also need to understand that you need to have a base case to terminate the function's call. So here's what I'll need to do in this case, right? Let's say we want to sum every value from 3 up to or down to 0, right? So I'll do something like this. So here I am doing result is equal to value, right? Value plus sum. So this will be called 3 minus 3. Value at first was 3, right? 3 plus 2, they call to 2, and then 1. So that's equal to 6. Okay, this is correct. All right. Let me explain what is happening here with recursive functions. So I will come. Okay, here's my board. We need this part here. I will erase this. This is something I did yesterday. In case you want to know what we studied yesterday, you can look at the day 89 video. So let me, I'm trying to bring my tablet, so I'll just, All right, sorry, I just went to get my tablet. Okay, so let's say, so we are trying to explain um, how recursion is done, right? So recursion is again a call to a function. So the function calling itself until um, until a certain condition is the base case, right, is met, and then we stop calling the function. So here is what we have in this case. We found we you know so we wrote this result sum values function, right? So our sum value function takes a parameter value which is an integer, and then we sum all the value up to 0, right, or down to 0 from the initial input. So here's what happens when we call this function. So I'll bring this here. I'll say some values, I'll call it SW or SV, right? Some values, we pass it 3, right? Now, this function, when it's called at this point and pass 3, and here's what happens. So the result variable is created, and then we check if the value is superior to 0. Of course, 3 is superior to 0, so we assign to the result the value plus a call to that function, right? So the function is called once again, but now with a different parameter, right? In a recursive function, we need to ensure that when we call the function, um, you know, when we call the function again, right? When we call the function, we need to pass it a new parameter, but of the same data type, right? So which means the value gets reduced by 1. So now we have 2. So here's what happens after calling this, right? We check if so results will become, I'll call this, so results will be 3 plus SV, right? SV 3 minus 1 is 2, right? Now this function gets called again right here. So we'll have another result again created, and then we do the entire value here, right? So a call to this function is simply going to create results. Result is equal to um, SV1, right? And then another call will happen here. We'll have results, sorry, um, not SV1 directly, but we have 2 plus SV1, and then another call again. We'll do 1 plus. Now in this case, when we get to the point where value is equal to 0, we just want to return the result, right? We just want to return the value. I mean, in this might be a little confusing, but let's just say return the value instead, right? So we are no longer going to call the function, we just return the value here. So let's bring this here. So we'll do 1 res is equal to, sorry, here we'll have res equal to 1 plus SV. Now if you do 1 plus 1 plus 1 minus 1 is going to be equal to 0, so SV of 0 is simply going to return 0. So in this case, we'll have res here will be equal to 1, right? Since we're adding with plus, right? So this will be 1 plus whatever this is going to be equal to 2, right? Plus, again, in this case, this is going to be 3, so 3. Here, when you calculate this is going to be 3 plus 2 plus 1 is equal to 6. So this is how the recursion happens, and we have to recursively call function and ensure that our base case is there to prevent any infinite loop. If we remove the base case, right? If we remove the base case, the function will call itself forever, right? So let me show you. Although I don't know if this will crash my computer, but let's You know what? If you want to try this out, just remove this base case here, right? And just remove this from here. Okay. Let's say you just do this. Okay. Let's you can see already. Okay. You can see we have an error here. Recursion error, maximum depth exceeded. So okay, this is cool. This did not continue calling itself. The program was smart enough to terminate the function call, which is really nice. Okay, that's very interesting. Let's see if there are any questions in the chat. Um, hello Dan. Trees the flash. Okay, trees the flash. Do not say. I square. I saw your videos. I saw your few videos. That was amazing. Hope you get 10 million soon. Thank you for providing this amazing course for free. Wow. Wow. Thank you, Sync. This is very encouraging. Thank you for your kind words. I really appreciate this. Thank you. Hopefully, I really get good at teaching and teach more people about the things I know. Right. All right. These messages are very encouraging. Thank you very much, my friend. All right. So let's continue. Um, we have more stuff to do. So that's a bit about recursion, right? Let's check on geeks for geeks whether they have more interesting, you know, examples. So a function, recursive call, right? Oh, the Fibonacci sequence. Now, this is a very, very, very interesting one. The Fibonacci sequence is actually um, a sum of every value, right? Let's say you have you are given a value and you want to sum down every value below that value. It's just something like this, right? But in this case, we need to call the function with another value, right? So we need to say n minus 1 plus n minus 2. Um, hmm. Fibonacci sequence. I actually linked this in the description in case you're wondering where I'm reading this from. So it's linked in the description below. I provided this code. So let's see how long this thing is. Okay, we can quickly go through and scan through this article. So the term recursion can be defined as the process of defining something in terms of itself. In simple word, it is a process in which a function calls itself directly or indirectly. So we have this nice meme here. As you can see, the the function keeps calling itself, so you can see the image. This is actually brilliant, right? If you let's imagine something like this. When I open when you open when you're when you are streaming something, right, with a software, or let's say you're in a Google Meet and you're sharing your screen. If you share your screen within the same screen, right, you will see an infinite preview of your screen down. It just keeps going, right? You don't see the end of it. So I think that's an example of recursion. Let me quickly show you if I can do this here. I will bring my streaming software here. Now you can see it keeps going down, right? There is no end to it. It doesn't show where it is ended, but you can see the screen is deep within itself. It's previewing the screen within itself, right? So this is an example of I would just say an infinite core, right? So with recursion, you can do something like this, but you also need to limit the call to the function. Otherwise, you will end up with an infinite call to the function. So, advantages of using recursion: a complicated function can be split down into smaller subproblems utilizing recursion. That is true. Sequence creation is simpler through recursion than utilizing any nested iteration. Recursive functions l- render the code look simple and effective. Okay, because there are no commas there, but anyways, we continue. So disadvantages of using recursion: a lot of memory and time is taken through recursive call, which makes it expensive for use. I'm not going to read everything, but let's see a Fibonacci sequence application now. A Fibonacci sequence, um, this is let's read what it is. So, a Fibonacci sequence in mathematics is a sequence in which each number is the sum of the two preceding ones. Aha. So that's the definition I was looking for. So you can use recursion to find the Fibonacci sequence of a number by finding the sum of the two preceding numbers of the actual number that is imputed into your function. So here is what we have. We define the function, right? And then if n is less or equal to 1, this is the base case. Return n, right? Return n. Otherwise, return a call to the function, right? Return the function n minus 1 plus the function call again, n minus 2. So whatever value is returned here will be passed in, will be, added to every value that is returned in the other call, right? So you can see, in this case, we'll have, if you passed it, okay, n times, this is 10. Okay, this is a long call. We'll have like a really long list of numbers. Well, anyways, so, and the base case here will help us terminate the function call, right? Otherwise, we'll keep calling it over and over again. Okay, so let's go ahead with this one and see. You can even find factorials of numbers, right, by doing this. In this case, right, we could actually return this by, saying, let me quickly erase this part. I'll say if result is equal to, if value is equal to 1, return value. If value is equal to 1 or is equal to 0, return the value. Okay, otherwise you can just say return value plus this. So return value plus this. So we can remove all this part here. So, oh, sorry, I wasn't showing this on the screen. So I was trying to restructure this function. So here you can see we are saying if value is superior to this, add the result to this place and then return the result, right? This is cool, but we can simplify this by saying if the value is equal to 0, right, we can return the value. Otherwise we can just return the value plus the sum value minus 1, right? So we'll return the sum of every value and pass it the function call again, right, with a parameter of value minus 1, right, and then we can just log this out and this will give us our function. So enough of recursion. Let's actually go back into our plan for the day, which is we'll still learn more about recursion. I will still, prepare myself properly to explain and give more examples on recursion. But for now, let me just increase this time to maybe an hour. 65 minutes is fine. Okay, so let's see our question. Now, to be able to solve our question, we need to do a quick recap on trees. We have to like go back and see what trees are, the basics of trees. For those who are not here when I did trees, so we have to learn more. I mean, learn again about trees. So, with trees, we have nodes that make up the entire tree. We have, okay, let me go here. Let me go to my screen. This section is actually on trees, so we can revise a little bit about trees. So let's see. Here we have, this is the structure of a tree. We have it like this. Okay. Now everything you see here is called, all the circles you see here is called node, right? These are nodes in the tree, and the topmost node is called the root node. Every node will have a value, right? So let's say this is like R, and then we have what's let's say S is here. Um let's say A. Okay, let's put C. You know what? Let me just use actual value. So this is going to be 2, or let's put 10 here. This is going to be, let's say, 5. We can put 3 here, and we can put 7 here. And here we can just do this like this. Okay, you know what? Let me just put just one value here. It doesn't really matter. So let's say this is 12. Now, this is our root, and every circle you see here is called a node, and each node is connected to a parent node by virtue of being the left or right child nodes, right? So this is the left. Okay, let's say this is the left child of the root node. This is the right child of the root node. Okay, and this here is the left child of this node, and this here is the right child of this node. Now, insertion of nodes in a tree is done in a specific order or in a specific manner. Now, when you look at this tree, you can see on the left side of the roots, we have values that are less than the roots, and on the right side of the roots, we have values that are superior to the roots. So let me remove all these annotations. Okay. Trying to redo this. Okay, so we know values that are on the left of the root node are less than the root node, and it is the same for every node within the left. So on this side, right, this is the left subtree. Going down from here to here, this is the left subtree, and from here to here, this is the right subtree. Although this node does not have child nodes, it means this node is a leaf node. So this is a leaf node. We have a leaf node. Leaf nodes are simply nodes that do not have left or child or right child nodes. So going down the tree, we have the left subtree, and going down the left side of the tree is the left subtree, and then on the right we have the right subtree. Now, when you see any node here, right, it means the node is a child or a parent of another node, right? So this node is the right child of the root node, but the parent to 3 and 7, right? So in a binary tree, you can't have nodes with the same values, right? Let's say, for example, here you can have another 12 here, or you can't even have a 7 here, because they are supposed to be unique values in the tree. So no duplicates. Every value in the tree has to be unique. So when you arrive when you arrive at a parent node, a node that is not a root node, and you see this node having children nodes, again the same thing will apply, just the way you inserted nodes from the roots, right? So on the left side of this node will be values that are less than this node here, which is 5, and on the right side of this node will be values that are superior to 5. The same thing will apply to this case, right? So beside 12, right, when you look on the left side, you will see values that are less than 12 but superior to the root node, right? So this will be, let's say, um let's put 11 here, and here we'll have something like 14, right? So superior or larger values can be on the right side, and smaller values will be on the left side. So that is really some basics of trees. And what's another thing we need to remember? I can't really think of something else. But for now, let's take a look at how we can implement a tree. So there is something else I need to explain. Now, these things you see here, like I said before, are called nodes, and the nodes have certain properties, right? So here, this is a node, and this node has a property called, so this node will have a value, right? The value of this node is 7. This node has a right and left child, right? Now, the left and right child here are not set, right? Meaning this node is a leaf node. This node does not have a left and right child. Since it doesn't have a left and right child, so the left and right will be null, right? By default, we set them to null. So when you create a node, right, this node that will be part of a tree has to have these properties: value, right, and left. Okay, so let's go ahead and see a basic implementation of a tree and print the nodes in the tree to see how it is done. So I'll come here and I'll write some code. So first of all, let's create a class for our nodes. I'll call this tree node, right? And our tree node will have some properties, but first of all, this is a class, so we need to define a constructor function. And for this function, when we create an instance of the tree node class, we need to pass it a value. So this is value, and we'll say self dot value is going to be equal to the value that we pass in here, and we will need to have the right and left properties. So say self dot right is equal to self. So I want to set this on the same line. Okay, just not to confuse you, we can put them on separate lines. Self dot left is going to be equal to none. Okay, so here's something else we need to do. Then we can start defining the tree itself, right? So I'll say class tree is going to be equal to, sorry, you know what, let's call this bts or b3. Okay, let's call it b3, and we need a constructor function. So we say yeah, so now our tree needs a root, right? So say self dot root. Come on, why am I typing like that? It's going to be none at first because it doesn't have any value or any node. The root in its basic form, right, is going to be none, right, in its initial form. So let's define a function to insert nodes in the tree. So here's how we'll do it. So we'll say define insert nodes. I like typing like this. Insert nodes and do something like, okay, this is a function that will take a value, right? Because we want to create a node, and we know by creating a node we need to provide that node with a value. So say new value, new node is going to be equal to the tree node. So let's define the tree node and set this to be the value here, right? The value. Okay, so then before we begin inserting nodes in our tree, we need to ensure that our tree has an actual root, right? So say if root is not none, right? No, sorry, if root is none, or if not root, sorry, self dot root here, self dot root. Okay, then we need to set root to be our new node. So self dot root should have the new node as its value, right? New node like this. Okay, then after doing this, we can then, okay, so after inserting this, we need to ensure that that is the only node we insert at that point. So we just run return to prevent any further actions. But when there is a root node, then it means we can set the root node as the next node, the new node we try to insert in the next insertion phase, as the left child or the right child of the current node. Meaning we have to traverse the tree and find a position where to insert the node, right? So we can say current node, current underscore node is going to be equal to self dot root. Come on, I don't know why I'm typing like this. Self dot root. Now we need to run an iteration to insert the value or the current node, the new node, into the tree. So meaning we have to traverse the tree until we find a spot that fits for us to insert that node into. So we'll say while this node is here, so while current node, right? While there's, okay, you know what? We don't need to do while current node. We need to do while this is true. Sorry. Now, while true will ensure we actually stop the iteration, the loop from continuing by ourselves, right? We need to define a case where the loop has to stop. Otherwise, where this is while true, we just keep running, right? So we need to check first of all if the new value we are trying to insert into the tree, right, is less than our current node value, right? So we'll say if value is less than the current node value, current node of value, right, then it means this is going to be either the left child of the current root or the left child of the left child of the root. So meaning if the root does not have a left child, we know every value that are less than every node's value that are less than the root value are going to be the left child of the root, right? So meaning if the current value is less than the root value, then we set this value as the left child of the root or wherever we reach at this point. But there's still a catch, right? Now, the only reason why we will set this value as the left child of the root is if the root does not have a left child yet. So we can say if current node, right, dot left is none, right, if the current node if the current node's left is none, right, then we can set current node dot left to be equal to our node, our new node, right, and then stop the iteration. Otherwise, if it's not, then we need to check the next left child of the current node, right? So we say current node then should become the current node should become current node that's left. That's left. Okay. So meaning here, while we are traversing the tree, right, and we get to this point, if the current node does not have a left child, then we set this current node dot left to be our new node, right? Otherwise, and we end the iteration here. Otherwise, current node should be equal to current node dot left. So meaning we are going to the next node, right? I think that this actually we need to check if current node, yeah, dot left is none, right? I think that's what I did here. Yeah, so current node dot left is none. Okay, that's good for now. So let's continue, and we'll do the same thing for the right node, right? So we need a left and right side of our tree, right? So if current node dot left dot right is none, then current node dot right should be equal to our new node, and then we break here. Otherwise, sorry, break, else we say current node is equal to current node dot right. Now with this method, with this steps, we'll be able to insert the nodes at their appropriate position. Now we need to define a function to print the nodes in a tree, even after inserting the nodes in the tree, right? So let's create an instance of our tree. So I'll say this is my tree. My tree is going to be equal to the BS tree. So B tree, okay, B tree. We don't need any value at this point, so I'll define some values here. I'll say values is equal to let me say 10, 14, 5, 6, 8, 3, and okay, this is a lot. Let's just put another 12 here. Okay. Here I can just make this a 16, right? Let's make this a 16 so that we can have a balanced tree. Okay, so we can iterate through the values here. So we can say for value in values, right? Let's call the my tree dot. So we created this. My tree has to have this insert node. So my tree dot insert nodes, and we want to pass it the value, right? So when we run this and there are no errors, it means we are on the right track. So let's try and print the values from the tree. So we can define a function and say, now printing the values from a tree is not as it's not the same step as it is with linked list, right? Traversal of nodes in a tree is done in a specific manner. So we have pre-order traversal and we have post-order traversal, depending on, and we have in-order traversal as well. There are at least 3 or 4 ways to traverse a tree. So the pre-order traversal is what we are going to use now, and it is also known as the depth first search, right? So the depth first search is to traverse the nodes down the tree, either on the left side or the right side, right, or the left subtree or the right subtree. So we can start from this point and traverse all the nodes on the left side, right, of this tree. And by left side, I mean when we get to this node here, we need to go on the left side of this node before going to the right side of this node. And the same thing will happen here. We'll go to the right side when we get to any node here. If this has a left child, we'll have to visit all the left children nodes before visiting the right children nodes. So this is called a pre-order traversal. Pre-order traversal. And also depth first search, DFS. So let's see how we can perform the pre-order traversal. Now, to perform this pre-order traversal, we need to use recursion, right? So I will write a function called pre-order traversal. I'll say define pre-order, okay, pre-order traversal, and this function would take a node, to be specific, the root node. So I'll say this is going to be an instance of a tree node, and we'll return a list of values, right? Now the reason why we need to return a list of values is because we need to take the values from the tree and add them to a list to show how they look at the end of the day. So in this case, we have 10. So let me represent this tree, right, and show you how the nodes will be printed out. So here we have the value 10. The first value in our list of values will be the root of our tree, because it is the first value we saw in the list. So I'll create a root here. So this will be 10. Let's just use this color. I'll say this is 10. 10 has left and right child nodes. Now 14 was the next value we saw, right? So 14 will be inserted on the right side because 14 is superior to 10. So 14 is here, and the next value we have is 5. So 5 goes on the left side. Then we have 16. 16 will be the right child of 14 because 16 is superior to 14. So we'll have 16 here. And the next value is 8. 8 is the right child of 5. So we'll put 8 here. And we then have 3. 3 will come here. 3 is the left child of 5. And 14 has a left child of 12. Now we can print. So traversing the tree, we'll have to go in this direction on the left hand side, right? So we'll visit every left child of the roots, and subsequently the left subtrees, right? And then visit the right subtree, and then the left subtree of the right child of the roots, and the right subtree of the right child of the root. So we'll start with 10, then we'll see 5, then 3, and then we'll see 8, 14, 12, and 16, right? The original order of our array is like this, of our list. Sorry, let's put it this way. So it was 10, 14, 5, 16, 8, 3, 12, right? But when we traverse the tree in a pre-order manner, meaning we are visiting all the left subtree and the right subtree after, then we can then return the nodes in this order. Please. So let me show you how this is done. So we can define the function. So at the end of the day, we want to return a list of we can return a list, right? Let's bring this here. I will import this class, this list module from the typing. So say from typing import list, Okay, right. So we have list here. Now we did a list. So I'll say results. Results will be here. So this is where we can add the values. So I'll say list as well. And here's what I need to do. So I'll say if the root node is not null. So if root node, as long as we are still in the tree, we can traverse the left side of the tree and the right side simultaneously. So we need to do results dot append root dot value, right? And then we call the pre-order traversal function for all the left child of the root node, right? So we can say pre-order traversal of the left side, right? So this is root dot left, and I'll explain how this is done under the hood. So let's pass in the result again as our second parameter, and we'll do the same thing for the right child nodes or the right subtree, sorry. So we'll say res oh sorry, we need root dot left, sorry, right, we need right, and then we'll pass in the result again, results like this. And yeah, so this is all we need to do. Then we can just create our own results here. I'll say I'll create an array. I'll say results, or let's call this node values, right? And set this to an empty array. Then we call the pre-order traversal function. We pass it our my tree dot root. So my tree dot root, and then we pass it the node values, and we print the node values to see what's inside. So we can say this is print node values. Okay, that's a mistake. All right, let's print this and see what we have in the console. Now you can see we have 10, 5, 3, 8, 14, 12, and 16. So if you look at this, right, it's still the same. Let me just copy it and show you the results. Let's put the results here. I'll increase this for you to see. Okay, when you compare these two, you can see we have 10 first, 5, 8, 5, 3, 8, 14, 12, and 16. So with the pre-order traversal, this is what happens. This will be our result, and there is more to understand what's happening under the hood, how this function is being called recursively, what happens during the recursive phase, right? So let's come back here and see how that is done. First of all, we check if there is a root value, right? So in this, let me erase everything that I have here, right? What are you looking for?
I'm looking for an empty rucksack, like these Adidas rucksacks, which I bought 3 of, so that Anita can carry her laptop home with some extra work to do from tomorrow.
Why didn't you come with
I mean, I bought 4 of these Adidas things. One I gave to
Sorry for the interruption. Um, so let's continue with what we have here. So I was trying to explain how the recursive function is called, right, for the pre-order traversal. So here's what happens. When we are pre-order traversing the tree, we start from the root node and we check if the root node has a value, right? If the root node has a value, then we proceed to do other stuff, right? Like adding the root value to our result array or our results list. So, um, now let's take a look at this. I will I will copy this part. I just want to take our tree here and use this as our example to explain what is happening. So I'll bring this down here, and this is our tree. Okay, so let's shift this tree to this part, have it here. Okay, so pre-order traversal, we start from the root node, right? Now, what really happens is when we recursively call this function, right, and pass it the left child, the same function is called, but this time around, we'll treat every node on the left subtree as the root node. Now, hear me, just wait a minute. Let me really go back to this. I just try to adjust this a little. Okay, hold on. I'm just trying to adjust this a little bit so that there's enough space for writing this function. Okay, so I'll just copy the function itself and paste it somewhere here. I'll paste Control Shift and V. So we have the function here like this. Pre-order traversal. Okay. So we can see what is really happening on the inside. Let's take a look at this. Okay, so here's our function, right? All right, so this is showing really well. Okay, we have this function defined here, right? And we have we say if root, right? If there is a root node, then proceed to do this, right? And when we proceed to do the other operations, I don't know if you can see this, but let me shift this entire thing to the side, right? And then bring this back here and increment this. Okay, I think this is better now. All right, so we first of all start with the root, right, which is here, and we have an array of empty, an array which is empty initially, and we want to add the values in the tree to that array. So our array here, I'll call this res. So res, okay, let's just create the array like this. So it's an empty array. Now when we start here, this part of the function is called, it says if there is a root, add the root value to our result, right? Result array. So we take this result, the root value, and then add result to it. So we add result to the root. We add the root's value to result. So this is going to be equal to 10. 10 is here. Then the pre-order traversal function is called once again, right? But this time around, it is called with the left side of the root value. So meaning we want to start on this side. Now here's what happens again. This other function is also called but separately. But here's what happens. Here, when we called root just left, everything on the left side of this root here will be called again with this function and in this same manner. So in this case, we'll have root dot left, the pre-order passed into the pre-order function called, but we passed into the pre-order the root dot left, so we pass it 5. So in this case, we come back here, the function, when the function calls itself, right? So let's treat this first function for this first portion of the recursive call, right, with the left side of the tree, of the root node. So root dot left is 5. So we check again if root, now 5 becomes the root, right? If root, okay, because this function is being called again, but with root dot left value. If root, right, if root is not null, if this current node is not null, then we need to add this current node value to our result value, right, or to our result result array or result list. So we take this 5 here, and then we pass it to the result array. Then we recursively call root pre-order left, so we call the left side of this root. Now mind you, when we call this is what happens, right? It also calls the pre-order for the right side of this current root. So I'm just treating the left side first of all before we start traversing the right side. So at this point, right, initially when we were here, we did something like this. We did pre-order traversal, I'll just call it POT, right? Root dot left is 5, and then we pass it our result array, and it had already 10 here, and we do POT for 14, right? For 14, so 14, and then we pass it the result array here as well. Now when this part of the function is called, POT is passed in. So we at POT 5, right? So we'll pass the left side of POT, which is the left subtree pre-order traversal. So which is 5. The left node of 5 is going to be 3. 3 will be called, right, and the results will be passed. In this case, we'll have 10 and 5, 10 and 5 like this, right? Now mind you, when we do POT like this, it also calls the left and right child of that node, right? So in this case, first of all, let's treat all the left child of this 5. I'll use a different color so that it is easy for us to visualize. So let's use a green color. So for 5 here, right, I'll just put this here like this to mark it that this is 5, or let's use an arrow, right? So for 5 we'll have something like this. We'll have POT, pre-order traversal, pass it 3, right, because 3 is the left of this 5. Again, POT 5, we pass it the array. The array was 10 and 5 at this point, right? And then the right side of 5 will also be called, right, which is this line here. So we'll have POT. The right side is 8, so we'll pass 8, and this will have 10 and 5. Now this function here will also be called for its own left and right child, right? For its own left and right child. So we'll say POT, right? So I'm just doing this for this other function. Let's use a different color again. So this is the recursion that happens under the hood. So POT of 3 and 5 will have POT here. So 3 dots left is null, right? So or none, and then we pass it 10, 5, and 3, right? This is none. So we'll do the same thing for here, for this function again. So we'll just use a blue color, right? We say POT of 8 dot right. So sorry, 8 dot left and right, right? So this will call for the left and right child of the current node. Meanwhile, these two do not have a left and right child node, and the condition is such that if the node is not null, right, recursively call this function. But because this node here, right, the right of 3, which is where this arrow is coming from, is none, then there is no need for us to continue the recursive call, right? If POT of none is passed, then there is no recursion happening. So we do POT. POT stands for pre-order traversal. I'm just using POT to shorten how many words I need to write. So here we have POT of, again, for 8, 8 does not have a left and right child, right? So this will be none of 10 and 5 and 3. So currently our result is built to have 3 values, which means we have traversed the left side of the tree, right? So we'll do the same thing for the right side of the tree. Again, POT will be called simultaneously until we reach the end, the leaf nodes. So this is what really happens when we recursively call the function, right? So it is something we that needs to be explained and understood for us to really be able to solve tree-based problems. Trees involve a lot of recursive function calls, right? So meaning we have to do recursion over and over again when it comes to trees. So mastering or understanding how recursion works is really crucial to solving tree-based problems. So let's read a question and solve that question using the techniques we just saw, right? So we have okay, this here is merging two binary trees. I want to solve a question that's already solved before. Okay. So you know what, let's start with this question. I'd already solved this question before and I'll explain how it is done. So we are given a tree, a root node of a binary search tree, and 2 integers, low and high. Return the sum of all nodes within return the sum of values of all nodes with a value in the inclusive range low and high. So we are given a tree, a root node, as the question says, and we want to sum all the values in this tree, right? Meaning we are going to traverse the tree and sum every value in the tree. That is really what the question is asking us to do, right? So thinking about this, the first thing that comes into mind is we need to traverse every node in the tree. And we know traversal of nodes in the tree is done with a pre-order traversal or any other traversal you know about. But I'm just going to use pre-order traversal, and then we can just go ahead and implement that. Now, I will create a file. I actually solved this function before, but I forgot to improve this. But here's what I did. I wrote a pre-order traversal function which adds every value in the tree, right, to a node array, right, a sum node. So this is sum node, and we are trying to, you see, first of all, let's really go back to the basics. Let me implement an example here. Let's say we want to define a function to add every values in the tree. We can simply do that by traversing with this function, right? But if we did root, if root, right, if root, and we add every node value to the result array, we can simply sum the values in the array, right? If we did print sum of nodes values, sum of node underscore values like this, we'll have the sum of the node values, which is 68. This is all right, but it is really not what we want to do, right? Hold on, give me a second. Let me All right, so um okay, so this is how we can sum the values. This is like one of the methods we can use. But you know, we want to do this within the function itself. We want to return the sum, right? Now, if we try to, do it here like this, then we need to really understand what needs to happen. So we have an array, right? Do we want to append the values to the array, or we want to append the values to a particular, we want to sum the values into the array? So one of the things I did then was to traverse the array in a was to traverse the tree with a pre-order traversal method by passing it a result array, of course. But this time around, I'm doing something a little different. I'm not adding values to the array per se. I'm adding values on top of one value in the array or in the results list. So this is what I did here. Um, Let me show you. So here I called the pre-order traversal, and I said if the node's value is between the low and high, then some nodes, which is an array, which is a list of values, will have its first value set to the node value and then increment it every time we call the function, right? And we just do pre-order traversal, and then we say total is our total. We call the pre-order traversal function, and then we return the total. But this is not really performant in terms of time complexity. This is quite slow, and we needed to improve this function. Now, coincidentally, I actually forgot to you know um to implement the improved version of this function, which is what I'm going to do now. So let's come here and implement this part. So this, I'm in the class. So let's say this is leads code 700. I think no 938. Okay, and then we can set the range sum. I think is range sum. What's the name of the function? Range sum bst, range sum dash binary search tree. Okay. Oh, it already exists. So let's do binary search tree improved. You know what? Just not to waste a lot of time. I'll just refactor redeem, copy this name here, and then I'll create a new file, paste this here, and say improved. Okay, so now let's write a proper recursive function to address every subtree and add those values to a sum at the end of the day. So this is what we need to do. I'll copy this part of the function as it is the original input. Alright, so I'll bring this here, and we need a tree node class, so I'll copy the tree node class here, and okay, so here's our tree node. This is the integer, and okay, so we are traversing a tree, meaning we are going to go through the left subtree and the right subtree of the tree that we are given. In other words, the root node. So we can first of all check if the root node has a value, right? So if root node is none, then since we are doing a sum, right, and something is none, we can just return 0, right? So if root node is none, then we can say return 0. Oh, return 0, right? But um if we had nodes in the tree, then we want to return some other values, the sum of every node in the tree. So we say um I'll create a sum nodes. I'll call the sum of nodes and set this to be equal to 0 at first, and then we say if the root dot value okay, if the root value is within the range of low and high, if low less or equal to the root dot value, right, less or equal to high. Okay, because the question says the range has to be inclusive, meaning our low and high, in this case low is 7, meaning every node that has a value that is equal or less than that is equal or superior to 7 can be added to our sum, right? And then for the high, the same thing, so less or equal to the high. So which means the current node the current root node the current node value is within the range. So we say some nodes, we just do plus equal root dot value, right? Now here's where things will become interesting. After doing this, right, we can simply say, oh, return some nodes, right? Sum of nodes, like this. Well, we know for sure we are going to return the sum of nodes at the end of the day, but if we did this, then we are just doing it for the root node, right? We are just returning the sum of values for the root node only. How about the left subtree and the right subtrees, right? So in that case, we then need to do something like this. We then need to check for every value in the range of low and high. If for every value in the tree, if the value is superior to the low boundary or the low side, the low the low part of the range, then we want to search um the left subtree of our current root, right? And then we'll do the same thing for the high point, which is this part here. So if low, right, is less than the current root dot value, right, then we need to say sum of nodes. Now we need to call this function, let's say range range sub range sum binary set tree, and then we'll pass it the root dot left. Okay, we pass it the low and high like this. Okay, now you can see one of the inputs here, we are recursively calling this function, but one of the inputs is changing. But when we call this function, right, all of this will happen, but meaning we will also return some node from this recursive call here. But where do we put this sum node? Well, we need to add it somewhere, right? We need to store the returned value of this function call. So meaning we have to do sum of nodes, plus equal the root node for every value in the tree that is superior to the low part. And then if the value is if the value of the node on the left side is within this range, then we add it to the sum node value, right? So we do this thing again. So we say if the root node, so we do it for the left side, right? So if high is superior to root dot value, Then we say sum of node is going to be plus equal root root dot left. Okay, we call the function again. Sorry. What did I just do here? Okay, I removed this part, so range sum here. So we call this function again, but we pass it the this time around we pass it the right side. So this is going to be right of this root. Okay. I think there's some what's this? High unfulfilled. Unfilled. What does this mean? We are still returning the high end. Okay, I don't think that's a big an error. It's just a syntax warning, I think. Okay, so let's see. At the end of the day, we can return the sum of nodes, right? Which is at this point. So let's do this. We'll say we'll call this function. You know what? Let's just run this in Leets code and see um, what we'll get. So I'll copy this function and paste it in Leets code. In Leets code here. So let's remove whatever was there before. We need to take this function away. Okay, I need to do it this way. I'll just copy this part. No, that's not working. So I'll copy the function properly. So root node here. Okay, and okay, so we have an error. Was the error here? So indentation. Oh, there was no indentation here. Wow, that's interesting. Range sum bst is not defined. What's that? Oh, sorry. Self dot. This is my fault. Okay, so it's the answer is wrong. So there's a few things that needs to change here. So let's see what happened. 25 instead of 32, which is very very strange. So if the root node is, we have low and high, right? Sum of nodes in the range of 3. Okay, I see where the problem is. This is not supposed to be there. This is not supposed to be there. So if low is this, then I mean if the root value or the current node value is within this range, right, we want to add that value to the sum of nodes. Otherwise, we check again. We check for values within this. For every low less than the root value, right? I mean, for every node that are superior to the low side, we need to check the sum of nodes in this range and add them to the sum. We need to call the range sum function once again and pass it the root dot left. Yeah, I think now this should work. Yeah, and it did work. So we can see the code was accepted, and let's run this and see how this will play out. Okay, the solution was fairly good. So we can see we're using the tree traversal. So we are pre-order traversing the tree and adding the result of the sum. So we are just performing this part of the function, right? So this is our actual logic. If the root value is none, then return 0. But if it is not none, then we can create a sum of nodes, right, and find out the low and left part. So if our current root value is within this range, and then if it is, then we add it to the sum of node and return the sum of node. Okay, sum of nodes in the tree. So let's move on to the next question, so we can find out this. So here's our next question. The next question is to check if the trees are the same. So we are given two trees and we need to find out if the tree is the same, right? If this tree here is equal to the other one. So okay, we need to do that now. Right. All right, so we can. I've actually done almost an hour. Okay, I need to finish all the questions now to be able to properly say that this section was actually good. Okay, so let's take a look at this part. I'll create a file and say same tree, right? So same tree. Okay, that's let's code 100. Okay, that's a perfect number. So actually this should have been here. Yeah, put it there. So I'll create leads code 100 new file. Let's create a new file. This is a new question we're solving for the first time. So this is going to be leads dash 100 dash same dash tree. We want to find out if two trees are the same, right? So let's quickly pass on to an explanation and what has to be done. So we do this for the first tree and the last tree. Okay, given the root of two binary trees, two binary trees, P and Q, write a function to check if they are the same or not. So two binary trees are considered the same if they are structurally identical and the nodes have the same values. Structurally identical means I think the same amount of nodes in the subtrees, right? And the nodes values themselves should be equal. So in this case, this tree is equal to this tree because the root values are the same, first of all, to begin with, and the value, they have the same amount of nodes. The left child of the root is the same as the left child of the second root, so in this case P and Q, and the right children are the same. So let's see what we need to do in this case, I'll copy this part of the function, input, and paste this here. Okay, you know what? Uh, I forgot to commit this. I need to do them separately so that we don't have the same. So git add git commit dash m. I'll say this is binary search tree leads code dash 938 okay. Then we can then go ahead and bring back the other function here. Okay, so we have it here like now. Okay, this is good. And then we bring this part back. I don't want this here, so yeah, so let's delete this too. I hate the fact that I can't actually directly change something. I don't know. Cancel this and replace, I think, replace all here. Yeah, remove that part. This is easier with VS Code. But anyways, that's question for another day, or an argument for another day. Maybe I don't know how to use this properly. So for two trees to be the same, they must have the same root, right? The same value in their nodes. And also, let's say if p, right, which is the current root, the current node, if p is none, right, meaning the current node is none, and q is also none, right? P and q is none, then this should be true, right? Meaning these trees are equal in this case. So return true. Return true. We need to check some edge cases, right? So that we are really sure of what we are doing. So if these two trees are none, then we can say the trees are equal. If one of them is, if okay, let's say else if p, right, p is none, p yeah, p is none. If one of them is none, right, then it means the trees are not equal. So if p is none, or q is none, okay, I'm just trying to solve this first before I pass on to the actual explanation. Just brainstorming, right? So if this is happening, then we can say return false, right? Return false. Okay. Now, if the value of this of p is not the same as the value of q, we can also return null. So if else if the p dot value is not the same as q's value, right? The current node dot value, q dot value, then we just return false, return false, right? Now these are the base case for us to actually begin traversing the um the trees, right? We'll traverse this and that simultaneously. Now traversing, we have to do a depth first search on the left subtree and then on the right subtree for each one of them. So we can say here, so when we pass this function, we will have to recall this function again. So let's say self dot is same tree, okay, self dot is same tree for q, or let's start with p dot left, and then we'll do the same thing for q dot left, right? And so if we did this, p dot left, this function will be called for the left side, right? And either true or false will be returned at some point. So this is really what we need to be concerned about. And so we have to return this. We can return this and self dot the same thing for the right. If both sides return true, then this will return true. Otherwise, we will return false if one of them is false. So let's say p dot right and then q dot right. Okay, so let's do this and see if we so if p, right, whether it's in the left or right side, so we start with the root. If the root is none for p and also for q, then we return true, meaning we have the same tree, right? They are structurally and in terms of value of their nodes equal. So this is one part. Now if one of the nodes from p or q is none, right, then we return false, meaning they are not equal, meaning in terms of structure they are not equal. But if the value, in terms of value, if they are structurally equal but the values are not equal, then we need to return false, right? And we call this function and pass it to the left and right side of the tree. So that is what I think, but let's try this out and see if this is going to work. So we'll call this copy, and before that we can then let's paste this here. Okay, this is not going to work like that, so let's indent it properly, return this and that. So let's run this and see. Okay, this actually worked. So we traverse both sides of the tree, which is very interesting. So really what we need to understand about recursion is we need to define our base cases first, right? And then we can choose to recursively call the function with the next or different with the next parameters, right? By this parameter I mean a different parameter but of the same type. So in this case we are calling p dot left and q dot left, meaning we are traversing the left subtree and comparing this part, right? We'll call this. In the case where we are done traversing the tree and we return either true if the p on the left and q on the left are the same, and meaning we reach the leaf node of each one of them, p and q. When we reach their leaf nodes we return true. Otherwise, if they are not the same, right, in terms of structure, we return false. If they are not the same in terms of value, we also return false. So we can submit this now and see what we get. Okay, you can see now this solution works, and I will submit this to the to let's commit this question. I'll say git dot commit git add git commit. So git add, let's clear the console, git commit, okay, commit dash m. I think I'm running out of time, and we'll continue the rest tomorrow. I've been streaming for long, so let's git commit. This is 3, or I call it BST, binary search 3, and this is lead code number 100, and we do this. So git add, git push origin main, git push origin main. Okay, so the solution to these questions will be available in the description. You can simply go to this link, right, and you'll get all the questions I've been solving so far, properly arranged, right, and you can see all the 2 pointers related questions will be here. All the doubly linked list, I think I didn't do much doubly linked list, but Q's questions will also be here. Linked list will be here, and what we just solved now, binary search trees, binary trees, will also be here, so you can have access to all of these and read the question, compare your answers to these ones, and we can just learn together, right? So this is about it, and I think I'm actually feeling dizzy now. Let me go and find some food to eat. So we'll continue tomorrow, and we'll see how things go from here. So let me check the chat if there are any questions. I think Divan. Okay, I don't know how to pronounce your name. Okay, the message was retracted. Hello, EW. Good afternoon. And who else? Bro, try odd string difference from late code. I think I'll do that tomorrow. I'm actually tired now. I want to go and rest a little, but I'll check the odd string difference. Let's see what question it is. Odd string difference, I'll find out here. Let's come here and paste the question here and see. So you are given an array of equal length string words. Assume that the length of the string s is n, right? So an array of equal length strings, okay, words, and the length of the strings is n. Each string word at I can be converted into a difference integer array, difference I of length n minus 1. Each string word I can be converted into a difference integer of length n minus 1, difference I. Okay, where difference I and j is word at I j plus 1. You know what, I'm not even reading this very well. I'll solve this tomorrow. I'll make sure I put the let me see. Yeah, I'll make sure I put this in the description, so that I can revisit it tomorrow. So let me put this here. I'll put this in the description to be solved, or I'll put this FAQ. Let's put FAQ here, and yeah, I'll just come to this tomorrow and solve it. All right. I'm really tired now. Hello, Comfort. How are you? Um, yes, there's more 10 more days to go. Okay. The challenge is done. I'm done for today. I'm actually tired, and thanks to everybody that was here. That was, you know, going through the. Oh, my friend is not here today. Let me check on him. Let's see. Here, we have a Discord server. If you want to join our Discord server, this is our Discord. We have here our general channel. You can join here. You can, discuss with others. Um, so let's see. Um, so the Discord server is here. You really just need to join, and I think, why does this look this way? Anyways, I think I streamed early today, and Ransom was not in the stream. That is unusual. Okay, let me remove this from here. Okay, let me put some question here. How do you tag a channel? Channel. All right. I think we'll continue tomorrow, and it's Rudra. Please, I will answer your question tomorrow, and take care, guys. Thank you for watching. I'll see you guys tomorrow.